choose lemmas. Suppose we have two irreducible representations, one denoted by gamma alpha and the other by gamma beta, and the dimension of the representation gamma alpha is say L alpha and that of gamma beta is L beta of a group G. And suppose we have a matrix M that satisfy the equation given by this, that is gamma alpha of Gk times M equal to M times gamma beta of Gk, where Gk is an arbitrary element of the group G. So if the matrix M and the irreducible representations gamma alpha and gamma beta satisfy this equation, then Schur's lemma says that M is either a null matrix, that means all elements of M are 0, or M is a square matrix with non-zero determinant. And in that case, gamma alpha and gamma beta would be equivalent representations. So what are the possibilities for a matrix M? M can have determinant 0 or determinant M not equal to 0. But if it satisfies this condition, then Schur's lemma says that either M should be 0 or it should be a non-singular matrix. That means it cannot be a matrix M which is not 0. That means at least one of the elements is non-zero and cannot have its determinant equal to 0. So Schur's lemma rules out the possibility of M not being a null matrix and having a determinant 0. So if it satisfies this condition, then either determinant should be equal to 0, in which case M should definitely be the null matrix. The possibility that M not equal to the null matrix and having determinant equal to 0 is what is ruled out by this lemma. So we now need to prove this lemma. So looking at this expression, if M is a null matrix, the left hand side is a null matrix and the right hand side is a null matrix, and therefore if M is equal to the null matrix, then this identity is trivially satisfied. And one more comment about the order of the matrix M. If we look at this expression on the left hand side, it is a product of gamma alpha with M. Gamma alpha is a matrix of order L alpha by L alpha. Now, if this matrix multiplication is well defined, that means the number of rows of M should be equal to the number of columns of gamma alpha. So that means number of rows of M is L alpha. Now, on the right hand side, if this matrix multiplication is well defined, that means the number of columns of M should be equal to number of rows of gamma beta. Now, gamma beta has dimensions L beta, that means the number of, so it's a matrix of order L beta by L beta. So the number of rows of L beta, gamma beta is L beta. And therefore, the number of columns of M is L beta. Or in other words, M is a matrix of order L alpha by L beta. And we have proved the first part of this lemma, that is, if M is a null matrix, obviously the left hand side and right hand side will be identically 0, and the null matrix, and therefore this is trivially satisfied. So we need to now consider the case when M is not a null matrix, and obviously M is of order L alpha by L beta, and for the time being we assume that L alpha is greater than or equal to L beta. So now we consider uh, uh, the representation gamma alpha of the group G in the vector space V alpha. So there will be associated basis vectors for this representation, and those basis vectors will be denoted by label psi 1, psi 2, etc. up to psi L alpha. Since gamma alpha is an L alpha dimensional representation, there should be L alpha basis vectors. So in the vector space V alpha, we have L alpha basis vectors denoted by psi 1, psi 2, etc. up to psi alpha that form a basis for the representation gamma alpha. Also remember, gamma alpha and gamma beta are taken to be irreducible representations. Since psi 1, psi 2, etc. Form a basis for the representation gamma alpha, the transformation of psi mu under the group action is given by this equation. Gi acting on psi mu will be the linear combination given by psi nu, then gamma alpha nu mu of Gi with summation over nu running from 1 to L alpha. Remember, since this correspond to the gamma alpha representation, the matrices that defines this linear combination are gamma alphas. Now we can consider a linear combination of these basis vectors psi 1, psi 2, etc. up to psi alpha in the following way. They consider psi mu times m mu j. So M is a matrix of order L alpha by L beta, and the linear combination defined this way will have one vector for each value of j. Since M is of order L alpha by L beta, there will be L beta values for j. So j runs from 1, 2, 3, etc. up to L beta. So we can define L beta vectors phi j this way. And we now consider the action of Gi on phi j. So Gi on phi j is simply Gi on the linear combination sum over mu psi mu m mu j. The group action is linear, so it can go inside the sum, act on this vector. So sum over mu Gi acting on psi mu times m mu j. Now psi mu is a basis for the representation gamma alpha, and the group action on it results in the vector given by this linear combination as we have just seen. So the linear combination is psi nu gamma nu mu alpha of Gi, because Gi is the group element that is acting on the basis vector psi mu, and the linear combinations are defined in terms of the representation matrices gamma alpha of Gi. So that's why we got this. So this is equal to this. Now these are all finite sums, so I can do the summation over mu first and summation over nu later. So that means I can write the summation over nu to the left of this expression. So we have sum over nu, then this vector psi nu, and then the remaining. So the remaining part is sum over mu running from 1 to L alpha. So that is this. Then gamma alpha nu mu Gi, then m mu j. Now from the rules of matrix multiplication, this is nothing but the new jth element of the product of the matrices gamma alpha Gi and m. So this is equal to gamma alpha Gi times m, then the new jth element. So new, and that's what we have written here. But now the condition that we start with is that these matrices and this representation, this matrix M and the representation matrices satisfy this condition, that is gamma alpha GKM is equal to M times gamma beta GK, and therefore this quantity is equal to M times gamma beta of GI. So we end up with this equation where this is replaced by M times gamma beta GI. So the new jth element of that is equal to new jth element of this. But now I can explicitly write down what that is. So this will be equal to the matrix product M gamma beta GI, but that can be written as a sum over k running from 1 to L beta. Then M, we need the new jth element, and therefore we should write M nu k, then gamma beta kj, because we need the new jth element GI. Again, writing the sum over k to the left, so we have sum over k running from 1 to L beta. Then sum over nu running from 1 to L alpha, then the psi nu M nu k, and then psi kj. But if we look at the linear combination that defines phi j, we see that this is nothing but the vector phi k, because linear combination is taken over the summation is over the index nu and the free index is k, and therefore this is nothing but phi k. So we have the result equal to sum over k running from L 1 to L beta phi k gamma beta kj gi. So the left hand side was the action of gi on phi j. So gi acting on the vector phi j reproduces or produces a linear combination of phi j's, and the number of phi j's is L beta. So this means that the set of vectors phi 1 etc. up to phi L beta spans an invariant vector space, invariant subspace of V alpha. It's a subspace of V alpha because these are all linear combinations of psi alpha which were a basis in V alpha, and therefore all these vectors should lie in V alpha, and therefore this vector space spanned by these vectors will also be a subspace of V alpha. And this equation says that if gi acts on any of these bases, any of these vectors phi 1 etc. up to phi L beta, then that produces a linear combination of these vectors only. So that means if we consider a space spanned by these L beta vectors, that space will be invariant under the group action, and the dimension of that space will be L beta because there are L beta basis vectors. So what we have achieved is the following. If we assume that the matrices M and the representations gamma alpha and gamma beta satisfy this condition, then we can define, starting with a set of basis vectors for the representation gamma alpha, then we can define a set of L beta vectors phi j defined by this linear combination with the matrix M. And then we see that the space spanned by the L beta dimensional space spanned by phi j are invariant under the action of the group. And this space is also a subspace of V alpha. So if we call this as the space spanned by, say if the space spanned by the vectors phi 1, phi 2 etc. up to phi L beta, if we call it as V beta, we see that V beta is a subspace of V alpha. Now, uh, gamma alpha is assumed to be an irreducible representation of G. That means it cannot contain a proper invariant subspace of the group G. But we have shown that B beta is a subspace of B alpha. But since gamma alpha is an irreducible representation, B alpha cannot contain a proper subspace which is invariant. So the only possibility then is that B beta is exactly same as B alpha. So, or in other words, we should have L alpha is equal to L beta. So that is the first result that we got. So with the condition that L alpha equal to L beta, M is a square matrix because M was a matrix of order L alpha by L beta. Now L beta is equal to L alpha, and then we can talk about a determinant. Then we can show that determinant of M in this case is not equal to 0. And this is because of the following. Suppose the determinant of M is 0. So then consider this definition, linear combination of psi mu's that gives phi j's. If determinant of M is 0, that means all phi j's that are obtained by this equation are not linearly independent. And therefore, since there are L beta, which is also equal to L alpha in this case, since there are L beta phi j's, all of them are not linearly independent, and therefore the space spanned by phi j's will have dimension less than L beta, but L beta in this case is equal to L alpha. So we will have a subspace spanned by phi j's with dimension less than L alpha, but because of this condition that we just got, this subspace should be invariant under the action of group G also. So this would directly result in phi j spanning a proper subspace of B alpha, which is invariant under the group action. But that is not possible because gamma alpha is an irreducible representation. So that means the condition that we started with cannot hold. That means determinant of M cannot be equal to 0. So what we have obtained now is the following. We started with a set of with an assumption that L alpha is greater than or equal to L beta, and using the initial assumption that M and gamma alpha satisfy the condition that we started with, that is this one, and using the fact that gamma alpha is an irreducible representation, we get the result that L alpha and L beta should be same. So in that case, we can also show that determinant of M is not equal to 0. So there is one more case that needs to be considered, which is what happens if L beta is greater than L alpha, because we have considered the case L alpha greater than or equal to L beta. Now what happens when L beta is greater than L alpha? For this we consider the initial condition that gamma alpha M is equal to gamma alpha Gi M should be equal to M times gamma beta Gi for all Gi. That is this condition. And then we take so this is true for any Gi, and therefore this is true for Gi inverse also. So we may consider the following equation. So Gi inverse M is equal to m gamma beta gi inverse. Now if I take the transpose of this equation, I will have on the left hand side m transpose times gamma alpha transpose of gi inverse equal to, on the right hand side, gamma beta gi inverse transpose times m transpose. But this is nothing but the adjoint representation of group G starting from gamma alpha. So that means m transpose, that is this, then the adjoint representation, that is gamma tilde alpha gi inverse, equals so this is equal to m transpose, then gamma alpha gamma tilde alpha gi equal to, and over here this is gamma tilde beta gi times m transpose, and this is the same as this because I can use gi in inverse instead of gi. And this is exactly what we got here. So gamma beta, so I am writing this to the left, so gamma tilde beta gk m transpose is equal to m transpose gamma tilde alpha gk for all gk's or all elements gk of the group G. So now in going from this equation to this, I did not use this intermediate step, but I could immediately say that the transpose of gamma alpha gi inverse is equal to the adjoint representation gamma tilde alpha gi inverse. I could also go this way, where I can say that this is satisfied for all gi inverse also, and then take the transpose, I will get this, but straight away this is simply the adjoint representation gamma tilde alpha of gi. On the right hand side I will get this equation, and simply interchanging the left and right hand sides, I will get this. But now this looks exactly like this equation with the role of gamma alpha taken by gamma tilde beta and m taken by m transpose and gamma beta taken by gamma tilde alpha. And in this case, for L alpha greater than L beta, we have obtained the result that either the determinant of m is not equal to 0. And coming back to this, this is similar. So here for L, so by the way, if I take the transpose of gamma beta and if gamma beta, so I can gamma beta are square matrices, and therefore if I take the transpose, its dimension is again the same, it is L beta, and therefore the dimension of the adjoint representation is also the same as the dimension of the representation gamma beta itself. So now this is similar to this equation, and the condition L alpha greater than or equal to L beta here correspond to L beta greater than or equal to L alpha over here. So then it would immediately say, using the same arguments as we used for getting the result that determinant m is not equal to 0 for this case, we now have, when L beta is greater than or equal to L alpha, we can see that this is satisfied only if L beta is equal to L alpha, and in that case immediately that determinant of m transpose is equal to 0, is not equal to 0. Now if determinant of m transpose is not equal to 0, determinant of m is also not equal to 0. So what we have proven is the following. If m is not equal to 0, then if it also satisfies this condition, then determinant of m is not equal to 0, and that L alpha is equal to L beta. So if L alpha is equal to L beta and its determinant is not 0, and the determinant of m is not equal to 0, that means m has an inverse m inverse. Then the condition that gamma alpha m equal to m times gamma beta can be written in the following. Since m has an inverse now, I can multiply from the left with m inverse. So I will have m inverse gamma alpha m equals m inverse m gamma beta. But this is the identity matrix, and therefore the right hand side is equal to gamma beta. So that means gamma beta is equal to m inverse gamma alpha m, where m is a non-singular matrix, a matrix with non-zero determinant. So that means gamma alpha and gamma beta are equivalent representations. And this proves the lemma. So stating it one more time, if gamma alpha and gamma beta are two irreducible representations of a group G, and M is a matrix which satisfy this condition, that is gamma alpha Gk times M equal to M times gamma beta Gk for all elements Gk of the group G, then M should be either a null matrix with all elements equal to 0, or it is a non-singular matrix, in which case gamma alpha and gamma beta will be equivalent representations as well. Now Schur's second lemma. Suppose we have a matrix M and an irreducible representation gamma alpha. If the matrix M commutes with all the representation matrices gamma alpha Gi of the group, then M should be a multiple of the identity matrix. Identity matrix of the same order as the representation. So the statement is a matrix that commutes with all the representation matrices of an irreducible representation of a group must be a multiple of the identity matrix. To prove this, we first assume that the dimension of the representation gamma alpha is denoted by L alpha, and we define a new matrix P, which is the matrix M minus lambda times the identity matrix of order L alpha. Now, whenever this lambda is one of the eigenvalues of M, then the determinant of this matrix P will be 0. That is because if lambda is an eigenvalue, it satisfies the characteristic equation that determinant of M minus lambda times the identity matrix is equal to 0. So that means if lambda is an eigenvalue of M, then P will be a singular matrix. Now, for any element Gi of the group G, consider the product gamma alpha Gi times P. So this is equal to gamma alpha Gi times M minus lambda times 1. So this is equal to gamma alpha Gi times M, that is this, minus lambda times gamma alpha times 1, But since this is identity matrix, this is simply equal to gamma alpha gi. But our assumption is that M commutes with all the elements, all the representation matrices gamma alpha gi. So that means this is equal to M gamma alpha gi. That is this condition. So we replace this by M times gamma alpha gi, and the second part remains the same. But then this can be written as M minus lambda times identity matrix times gamma alpha gi. But M minus lambda times identity is again P, and therefore we see that gamma alpha gi times P is equal to P times gamma alpha gi. So now we consider the Schur's first lemma, which says that if we have a matrix M that satisfy the condition that gamma alpha gi times M is equal to M times gamma beta gi for all gi in G, then M should either be the null matrix or it should be a non-singular matrix. So now consider this equation. Here alpha and beta are the same. Then so this would then immediately say that M should either be a null matrix or a non-singular matrix. But now consider the case where determinant of P is equal to 0, and that happens when this lambda is one of the eigenvalues of M. So in such case, P is determinant of P is 0. But according to the Schur's first lemma, if P satisfy this condition, then P should either be a null matrix or a matrix with non-zero determinant. So the only possibility for P to have a determinant equal to 0 is for it to be the null matrix. That means for a lambda, which is the eigenvalue of M, P has 0 determinant, and in which case, since P satisfies this condition for all GIs, P should be a null matrix. In other words, P is identically equal to 0. But P is M minus lambda times identity, that is 0. So that means M should be equal to lambda times the identity matrix. That is exactly what Schur's second lemma says. If a matrix commutes with all the representation matrices gamma alpha gi, then that matrix should be a multiple of the identity matrix. And here we know that this multiple is in fact the eigenvalue of the matrix M. The orthogonality theorem of irreducible representations. Consider two irreducible unitary representations, gamma alpha and gamma beta. So unitary representation means the individual representation matrices corresponding to each group element denoted by say gamma alpha gi and gamma beta gi are all unitary. That is the adjoint of gamma alpha times gamma alpha for a particular element, and that will be equal to the identity matrix. So given two irreducible unitary representations, gamma alpha and gamma beta of dimensions L alpha and L beta respectively, we can construct the following quantity. So consider gamma alpha the pmth element of gamma alpha gi and take its complex conjugate. then multiply it with the qnth element of gamma beta of gi. Then take the sum over all group elements gi of the group, and that is the quantity that I have written here on the left hand side, and that will be equal to G divided by L alpha times delta PQ, the Kronecker delta PQ times Kronecker delta Mn, where G is the order of the group G. So that is, if P is not equal to Q, or if M is not equal to N, then this quantity is 0. And if P is equal to Q and M is equal to N, this quantity will be equal to G divided by L alpha. Now we can also construct a similar quantity if gamma alpha and gamma beta are two inequivalent irreducible representations. Then the quantity constructed this way, but in the second case, instead of gamma alpha qn, we take gamma beta ln, and that will be equal to 0. So if these two are the same irreducible representation, then this quantity is equal to G by L alpha times delta PQ times delta Mn. And if they are different, if they are inequivalent, gamma alpha and gamma beta are inequivalent, then this quantity is equal to 0. Now these two can be combined and written in the following way. Say gamma alpha Pm of Gi star, then gamma beta Qn of Gi, then sum over Gi will be equal to G by L alpha delta PQ delta Mn, then a delta alpha beta. So when alpha is not equal to beta, this becomes automatically 0. So these two cases are covered here in this equation. Remember, while writing this equation, we have assumed that if alpha is not equal to beta, then gamma alpha and gamma beta are inequivalent irreducible representation, unitary representation. Now we now consider the proof of this statement. For that, we first consider a matrix X, an arbitrary matrix X of order L alpha by L beta. Then we define a matrix M which is obtained by consider gamma alpha Gi times X times gamma beta Gi inverse. Now gamma alpha Gi is a matrix of order L alpha by L beta, L alpha by L alpha. X is of order L alpha by L beta, and gamma beta is of order L beta by L beta. And therefore, this matrix multiplication involving these three matrices is well defined, and the number of rows of the resultant matrix will be L alpha, and the number of columns of the resultant matrix will be equal to L beta. So the result is a matrix of order L alpha by L beta. Now we consider summation of this quantity over all elements Gi of the group. So Gi in G, and the resulting L alpha by L beta matrix will be called M, and that is what we have defined here. Now we multiply this matrix M from the left with gamma alpha Gj. So writing the explicit expression for the matrix M, we have gamma alpha Gj, then sum over Gi, gamma alpha Gi x gamma beta Gi inverse. Matrix multiplication is a linear operation, so this can go inside and multiply this. So we have sum over Gi gamma alpha Gj, so that is this guy, and then this gamma alpha Gi, then X, and then gamma beta Gi inverse. Now, gamma alpha is a representation, and therefore gamma alpha Gj times gamma alpha Gi is simply gamma alpha of Gi Gj, sorry, Gj Gi. And then we have X and gamma beta Gi inverse. Summation is over Gi. Now we remember the rearrangement theorem. So that means if I multiply every element Gi of the group G by one of the elements Gj, then it again produces all the elements of the group but in a different order. So that means instead of if Gj, Gi can be written as the element Gk, instead of taking summation over Gi, I can take summation over Gk. It will also cover all the elements in the group. So now we define Gk to be Gj Gi, then summation over Gi can be written as summation over Gk. So the first matrix is now gamma alpha Gk, then X. But then Gi inverse has to be represented in terms of Gk. And since Gk is equal to Gj Gi, we have Gi equal to Gj inverse times Gk, and Gi inverse is equal to the inverse of Gj inverse times Gk, which is Gk inverse times Gj inverse inverse. But inverse of Gj inverse is nothing but Gj, so we will have Gi inverse equal to Gk inverse times Gj. So we end up with summation over Gk, then gamma alpha of Gk, then X, and gamma beta of, instead of Gi inverse, Gk inverse times Gj. But now again, gamma beta is also a representation, which means that gamma beta of Gk inverse Gj is equal to gamma beta of Gk inverse times gamma beta of Gj. So we will end up with this equation. So that means gamma alpha Gj m is equal to, then summation over Gk, gamma alpha Gk X, then this is written as this, and therefore we will have gamma beta Gk inverse times gamma beta Gj. But see, the summation is over Gk, and this quantity is independent of Gk, and we can also write this as this summation times gamma beta Gj. But this summation, if we look at the definition of the matrix M, nothing but the matrix M, and therefore we have this equal to M times gamma beta Gj. So what does that mean? So we have on the left hand side gamma alpha of Gj times M is equal to M times gamma beta of Gj, where gamma alpha and gamma beta are irreducible representations of the group. Then we can use Schur's first lemma. It would say that if M and the representation satisfy this condition, then M should either be a null matrix or the determinant of M should be non-zero, in which case gamma alpha and gamma beta will be equivalent representations. Now if so that means if gamma alpha and gamma beta are inequivalent representations, the only possibility according to Schur's first lemma is that determinant of M is not 0, but in that case correspond to M being the null matrix. Okay, so if alpha and beta, sorry, gamma alpha and gamma beta are inequivalent irreducible representations, then M is equal to 0. However, if gamma alpha and gamma beta are the same matrix, the same representation, so that is alpha equal to beta, then we can use Schur's second lemma, which would say that M should be a multiple of the identity matrix. So it should be some factor lambda times the identity matrix. Okay, so that means if we restrict ourselves to a set of irreducible unitary representations of group G, such that gamma alpha and gamma beta are inequivalent whenever alpha is not equal to B, then when alpha is not equal to B, this matrix M should be null matrix, and if alpha equal to B, M should be a multiple of the identity matrix, which can now be written in the following way. So M is given by this sum, which is summation over Gi in group G, gamma alpha Gi x gamma beta Gi inverse should be 0 if alpha is not equal to B, and should be a multiple of 1 when alpha equal to B. So I can write it as delta alpha beta lambda times the identity matrix. Now we take the case when alpha equal to beta. So gamma alpha and gamma beta are the same representation. And then I take the trace of this equation. So we have, so when alpha equal to beta, this will be 1. So the trace of sum over Gi gamma alpha Gi x gamma alpha Gi inverse, because beta is now equal to alpha, is equal to trace of, the right hand side is simply gamma lambda times identity matrix. Now, a trace of a sum of matrices is simply sum of the trace of the matrices. That is, trace of A plus B is trace of A plus trace of B. And therefore, the trace of this sum is equal to sum over Gi of trace of this individual matrices. Trace of gamma alpha Gi x gamma alpha Gi inverse. And that should be equal to trace of lambda times identity matrix. Now, if we have a scalar number multiplying a matrix, trace of lambda times A is equal to lambda times trace of A, and therefore trace of lambda times identity matrix is simply lambda times trace of the identity matrix. Now this identity matrix is of order L alpha, so it's an L alpha by L alpha matrix, and therefore its trace would be simply L alpha. Remember, a trace of a matrix is the sum of the diagonal elements of the matrix, and there will be, for an identity matrix, the diagonal elements will all be 1, and there will be L alpha such diagonal elements in an L alpha by L alpha matrix, and therefore trace of identity matrix of order L alpha is simply L alpha is equal to L alpha. So that's what we have written here. Now on the left hand side, we have trace of gamma alpha Gi x gamma alpha Gi inverse. Now we use the property of a trace, property of the trace, that trace of ABC is equal to trace of CAB. So I have this equal to A, this equal to B, and this equal to C. And this should be equal to the trace of the product obtained by taking this to the left hand side of that. So that is equal to trace of gamma alpha Gi inverse. I have taken this guy over here, and then gamma alpha Gi and then x. But gamma alpha is a representation of the group, and therefore this is equal to gamma alpha of gi inverse times gi. So we have sum over gi trace of gamma alpha gi inverse gi times x is equal to lambda alpha. Now gi inverse gi is the identity element, and gamma alpha of identity element is simply the unit matrix of order L alpha. So let me write it as 1 L alpha, means the unit matrix of order L. So here I have the, so this is equal to E, and gamma of E is simply the identity matrix. The identity matrix times X is simply X. So on the left hand side, I have sum over gi, trace of X equal to, on the right hand side, lambda times L alpha. Now trace of X is independent of gi, and we have, say, G elements in the group. So this summation is equal to trace of X plus trace of X and so on, G times. So that is equal to G times trace of X. So the left hand side is G times trace of X, the right hand side is lambda times L alpha. Or in other words, lambda is equal to G by L alpha times trace of X. So far we have taken X to be an arbitrary matrix of order L alpha by L beta. Now we consider a special case of X. So X is a matrix whose elements are all 0 except for say X, M, N. So except for the mnth element, all other elements of the matrix X are 0. But then it can be written as XRS. The RS element of X can now be written as delta Rm delta Sn. So that is, when R is equal to M, this will be 1 and will be 0 when R is not equal to M. Similarly, it will be 0 if S is not equal to N, and will be 1. So if I take the choice XRS equal to delta Rm delta Sn, this means X is a matrix whose mnth element is 1 and all other elements are 0. Now if we also take alpha to be equal to B, then L alpha is equal to L beta, L alpha to be equal to beta, then L alpha is equal to L beta, and therefore the matrix X is now a square matrix. And we can compute its trace, and trace of X will now be equal to sum over sum over R running from 1 to L alpha of X R, the diagonal element of X. Now using this formula, X R is equal to delta Rm delta Rn. Now the summation over Kronecker delta can be easily done. So we use this Kronecker delta. So after summation, the R here will be replaced by M. So we will have delta Mn. So trace of X is equal to delta Mn. And substituting this here, for this particular choice of X, we will have lambda equal to G by L alpha times trace of X, which is delta Mn. Now going back to this original equation that we got, that is sum over Gi gamma alpha Gi X gamma beta Gi inverse equal to delta alpha times lambda. For the particular choice that X is equal to the nth element of X is 1 and all other elements are 0, we can use the corresponding expression we got for lambda here, and we can explicitly substitute the value of X here, and we end up with this equation: sum over Gi gamma alpha Gi X gamma beta Gi inverse, and if I take the pqth element of that, on the right hand side I will have G by L alpha, delta alpha beta, delta mn. Then we had the identity matrix. We now need to take the pqth element because we are taking the pqth element on the left hand side. And by the way, this expression for lambda is valid only when alpha equal to beta. Whereas when we wrote this here, this was taken in general for alpha is not equal to beta as well. And this expression will hold here because when alpha is not equal to beta, this factor of delta alpha beta makes the right hand side at 0 irrespective of what we use for lambda there. And therefore we can generally put lambda equal to this value, which is true only for alpha equal to beta here as well, because whatever be the value we use for alpha not equal to beta case here, the factor delta alpha beta makes the right hand side 0. So it is okay to use this particular form of lambda here in the general case when alpha is not equal to beta as well. But now the pqth element of the expression on the left hand side can be obtained using the expansion of the matrix product. So we will first have sum over Gi. Then we have two products, gamma alpha times x and that times gamma beta. So we will have two summations and the summation variables will be written as r is equal to 1. For this product, I will use r as the summation index, and the summation index will run from 1 to L alpha for that. So that will be gamma. So I am taking pqth element. So I will have gamma alpha pr times xrs times gamma beta sq. So r and s are summation indices and s will run from 1 to L beta. And that is equal to, on the right hand side, G by L alpha, delta alpha beta, delta mn, and the pqth element of the identity matrix. The pqth element of the identity matrix is simply delta pq. But now we have xrs here and we know exactly the form of this matrix X because we have used this formula for lambda, which is valid when we choose xrs to be equal to x. So we have to replace xrs by this form here. So we have delta rm times delta sn in place of xrs. So the summation over r and s will now be simple because it is a summation over Kronecker delta functions. So we just need to replace r by m and s by n in the remaining factors. So we have sum over Gi, then gamma alpha p, and instead of r I should write m. So gamma alpha pm Gi. Then here in gamma beta sq, instead of s I should write n. So gamma beta nq Gi inverse, and that is equal to G by L alpha, delta alpha beta, delta mn, and delta pq. Now from the property of the representation matrices, we know that gamma beta of Gi inverse is simply inverse of gamma beta Gi. Now we have also said that these representations are unitary. So the inverse of a representation matrix is simply the adjoint of the representation matrix. So gamma beta Gi inverse is simply gamma beta Gi dagger. And if I take the nth element of that, so nth element of gamma beta Gi inverse, then we will have the corresponding nth element of this quantity. So that is gamma beta Gi dagger and the nth element of that. But then that is equal to the complex conjugate of qnth element. So we may write this as gamma beta qn of gi the whole star. And substituting this for this here in this equation, we will get sum over gi gamma alpha pm of gi times gamma beta qn of gi star equal to g by L alpha beta delta mn and delta pq. Now remember, the quantities on the right hand side are all real. G is a number, L alpha is an integer number. These are all real numbers. So if I take the complex conjugate of this equation, the right hand side remains the same. And if I take the complex conjugate of the left hand side, I will have a star here, and the complex conjugate of complex conjugate is the quantity itself. So the star will be gone from this. And this equation is exactly same as the statement of the theorem, the orthogonality theorem. So the orthogonality theorem is simply obtained from this equation by taking the complex conjugate.